Let's discuss about the electric field strength due to an electric dipole at equatorial position. So, first of all, let's again talk about this electric dipole. So, when two equal and opposite charges, so here both this positive and minus q, this both have equal magnitude. Charges are separated by some distance. In this case, it will be 2L because from the center it is L and again it is L out here. So total distance will be 2L. So that configuration is electric dipole. And the strength of electric dipole is always given by electric dipole moment, which can be mathematically defined as the product of either of charges. So you can take any one magnitude and multiply by the distance between them. So in this case, the distance is 2L. So we are multiplying it with 2L. So this gives the electric dipole moment. So it is a vector quantity and the direction will always be from a negative to positive charge. So that means the dipole will be, so if say if I consider this point to be B and A, so the dipole will be directed from B to A. So that will be the direction of electric dipole moment. So let's give this equation number 1 as we are going to use this equation later on. So the next thing is we are going to find electric field strength at P. So for that, what we need is we need to bring one test charge at this point P, and this P point out here is called equatorial position for this electric dipole. So if we have to define equatorial position, so that is the that is any point which is perpendicular to the axis of the dipole. So in this case, you see this dipole which is separated by 2L distance. So this O, which is uh, we can say which is dividing the length by which the dipole is being separated into two equal halves, L and L. So this is the center point O. So above this center point anyway, which is perpendicular to this axis, so we call it as an equatorial position. So we have considered this point. You can consider any point in this line, so which is perpendicular to the axis of this dipole. So that is our equatorial point, and then we are finding the electric field strength at this position P. So that basically means we need to bring a test charge out here and see how electric field strength is experienced by the test charge out here at P because of this positive and this negative charge. And then we will use the principle of superposition and we'll find the individual electric field strength due to this plus Q and minus Q. And by using the principle of superposition, we'll take the vector sum in order to get our final electric field strength or net electric field strength at this P. So to begin with that, first let us begin by examining how this P, the test charge at P, is going to experience force due to this plus Q. Okay, so then the test charge which we consider is basically will be a positive in nature. So that means this positive charge out here at A is going to push this test charge in the line joining these two charges. So that basically means the force which is acting on this test charge will be in this direction. Okay, so it will be pushed in this direction. So this will be the electric field strength direction. Okay, so this will be the electric field direction. Let us give this name as EA because this is the electric field strength due to positive charge at A. So we are giving it a name as EA. Similarly, if you see out here is a negative charge, so then the test charge out here at B is going to get pulled towards this minus Q towards B and along the line joining these two charges. So then our direction of the electric field strength due to minus Q at B will be directed. Okay, so let me remove this one first. Okay, so will be directed towards B, so it will be like this. It will be in this direction, and then we are going to give this name as EB since it is because of minus Q which is placed as B, and just for the name we are giving it EB. Okay, so to see how much electric field strength magnitude will be there at P because of the positive charge at A, we need to find the distance between this positive charge and this point P, which can be obtained using Pythagoras theorem, because if you see this triangle A, P and O, then you will see this is a right angle triangle where this angle O out here will be 90 degrees. So you know this according to Pythagoras theorem that hypotenuse squared will be sum of perpendicular squared and base squared. In this case, so hypotenuse will be the side opposite to this 90 degrees, so which will be your AP, which we are finding, and it will be root over, so perpendicular, if you see this r will be the perpendicular, so that will be r squared, and if you see this base, it will be this one L, so this will be L squared. So that basically makes this as r squared plus L squared. So, and similar, you see that it is symmetric, both the triangles are symmetric, so that gives us this distance out here, BP is also what, our r squared plus L squared. So once we get this distance, we can write the equation for electric field strength due to both positive Q at A and negative charge at B. Okay, so let's write it down. So first let me write it as electric field strength, first we will write due to plus Q at A, electric field strength at P. We are finding electric field strength at P, and first we are going to write due to positive charge at A. So we will give this name EA. Okay, and the equation we know, it is written as K Q by the distance between the charge and the point where we are finding the electric field strength. So that will be your r square plus L square, and we know it is squared out here because it is KQ by r square. So in this case, r is r square plus L square. So this eventually, if we cancel out the root and the square, so we will get this KQ by r square plus L squared. So give it as equation number 1. Similarly, now here, if I am to write about the electric field strength at P due to minus Q at B, therefore I can write EB. I'm giving name as EB because minus Q is placed at B. So EB will again be KQ by root over r square plus L square squared, because in this case also, if you see the distance between the charge minus Q and P, it is again r square plus L squared. So here also the square root and the square will be cancelled out, and we will get r squared plus L squared. So now you can give this as equation number 2. Okay, so now we need to find the net electric field strength because of this EA and EB. Since both EA and EB are acting on the same point, so that means there will be one resultant. Okay, so there are various way of doing it, but let me choose this way. I will consider one horizontal line from here, this imaginary horizontal line. Okay, so let us make this with a dotted line out here. Okay, so this is our imaginary horizontal line. So by symmetry, if you see, we can prove these two triangle congruent, and since all the lengths are equal, so therefore if it is congruent, then its corresponding sides are also going to be equal. Okay, so if this is theta, then you can assume then this will also be theta. Okay, and if it is theta, then this angle out here will also be theta because they are alternate angles. So if you see it is like this, so if this angle is theta, so this angle also will be theta, so it's an alternate angle. And if it is theta, then this angle out here will also be theta. Why? Because they are vertically opposite angle. Okay, so again, if you see this angle theta, so that makes this angle also to be theta. Because why? Because again they are alternate angles. So now we know that this angle is theta, so let's resolve the component of EA and EB to get the net resultant magnitude. So you know this EA can be resolved into its two components. So that is one component we are going to, okay, so let me make it a different color so that it will be easier for us to resolve. Okay, so let's say in this direction we have this component out here, and in this direction there will be another component out here. Okay, so let me first remove this one. Okay, so I will remove EA from here. I will write this EA out here because, okay, now I'm going to resolve it. So in the perpendicular direction there will be one component, and since this angle is theta, so this angle is also going to be theta. So the side which is associated with theta can be written as EA cos of theta, and the side which is perpendicular to this Ea cos theta can be written as Ea sin theta. Okay, and now similarly, let's do it with EB also. So here you see EB, it can also be resolved into its two components. So okay, now this will be my one component in this direction, the other component will be in downwards direction. Okay, okay, so then again, since you can see this angle out here is theta, so this angle out here will also be theta. Okay, and then if it is theta, this component will be given by EB cos theta, and the component which is perpendicular to this EB cos theta is given by EB sine of theta. Okay, so this is how our electric dipole at equatorial position looks like after resolving the components. So let's solve it with the help of symmetry, because it will make our job easier. Because see, if you see the equation number 1 and 2, if you see this equation number 1 and 2, you can say that EA equals EB. Okay, so that means EB and EA are equal in magnitude. Okay, and then if EA and EB are equal, so we'll just write it as E, because both of them are equal, say. Now since EA sin theta and this EA is equal to this magnitude EB, and both are linked with the sin theta, so and they are opposite in direction, so then this, since it is since being this EA sin theta component being equal in magnitude and opposite in direction, we can cancel this out, because they are equal in magnitude and opposite in direction, so therefore it cancel out by symmetry. So only what is remained, EA cos theta and EB cos theta, and see they both are in same direction, so therefore to find the net electric field strength at P, we simply need to add these two components. Okay, because why? Because they are in the same direction, and if you ask, then the net electric field is, okay, the net electric field strength will also be directed in this direction. So because both EA and EB cos theta are in the same direction, so that is going to contribute for the net electric field, and net electric field E net will also be directed in the direction of EA cos theta and EB cos theta, and then this E net can be obtained by the sum of EA cos theta and EB cos theta. So looking at the direction, both EA cos theta and EB cos theta are in same direction. This EA and this EB cos theta are in same direction, so E net will be simply added. Okay, E net can be obtained by adding EA cos theta and EB cos theta. Since EA and EB are already equal and we have defined it to be E, so then I can write E net as E cos theta plus of E cos theta. Okay, and then E net can be obtained by 2E cos theta, where we know that E is already, we have already written the equation for E, so that makes E 2E. From equation 1 or 2 you can use any equation, so it will be KQ by R square plus L square. And then what is cos theta? So cos theta will be simply base upon, okay, base by hypotenuse, it will be hypotenuse. Okay, so now we will find the base and hypotenuse from this triangle POB. So hypotenuse will be this root over R square plus L square, and then the base will be this L, the side which is associated with theta will be your base, and perpendicular to your opposite to the 90 degree will be your hypotenuse. So the hypotenuse will be root over, so from this triangle, from triangle say OPB, so hypotenuse will be your root over R square plus L square, and your base will be your L, so which we are going to use in this equation. So therefore what are we going to get? So E net will be your 2KQ, so R squared plus L squared, and then what is our base? Base is our L. So what is our hypotenuse? Hypotenuse is root over R square plus L square, and you know root over can be written as to the power half. Okay, so now you can see this base are same, R square plus L square and R square plus L squared. So that means it will have power 1. When base are same, the power should be added. So by that, what we are going to see that it will be your KQL, KQL, and then what will be added? R square plus L square are same, so the power 1 plus half. So that will give me to the power 3 by 2, because the base are same. Okay, base are same, so the power is added. We also know from equation 1, so from equation 1, which we have already defined, that P, electric dipole moment, is uh, product of charge with the distance between them. So here is Q and there is 2L out here, so simply which we can replace it by P. So E net will be your KP by R square plus L squared 3 by 2. Okay, so this will be our equation. After solving, we got this one. Okay, so now we are going to write this equation for an ideal dipole. For an ideal dipole, what we consider the R, the point, the distance from the axis of the dipole to be very bigger than the L. So that means what we are saying, this OP is very greater than this AO or BO. So that distance. So uh, because of that, we can we can neglect L. So if we neglect L in this equation, so what we are going to get, E net equals KP. So this will be your R square plus L can be ignored, so L can be neglected, so it will simply R square. So 3 square by 2. So if I remove the bracket, E net will be your K, P and R squared into 3 by 2. So this 2 and 2 get cancelled. What I'm going to get, E net is equals to K, P by R cube. Okay, so this will be our final equation after considering an electric dipole. And lastly, let's write this in a vector form. Okay, so writing in vector form, let's see both the direction of electric field strength and electric dipole moment. So here if you see, then the net electric dipole is directed here, so which is directed here like this, which is in x, positive x direction, but our dipole is directed from negative charge to positive charge. So that means our dipole, our negative charge is here and the positive charge is here. So my dipole is directed here and the electric field is directed here, so they are opposite in direction. So since they are opposite in direction, what I can use, a vector sign out here, and with a negative sign I will show that this dipole moment direction is opposite to the electric field strength. So this will be my final equation in a vector form.